Breathing at high altitudes. If you have ever hiked or lived to high altitudes in the mountains, you surely have noticed how short a breath you get. This occurs because the air is thinner, so each breath contains fewer oxygen molecules than at sea level. At the top of Mount Everest, the pressure is only one-third atmosphere. Air contains 21% oxygen and 78% nitrogen, and an average human breath is 0.50 liter of air, just a half liter of air. At the top of Mount Everest, A. How many oxygen molecules does each breath contain when the temperature is minus 15 degree Fahrenheit? And B. What percent is this of the number of oxygen molecules you could get from a breath at sea level at kind of the same temperature, minus 15 Fahrenheit? Okay, so this question is from the thermophysics topic, where we will learn a lot about the relationship between the pressure, the volume, and the temperature of an amount of gas. And usually we consider them as the ideal gas. So let's see, where should we start? We should start from like what they ask us to do, right? First, the first question. They ask us to find how many oxygen molecules. Okay, so I will say that whenever you start a problem, try to figure out what the questions is asking us to do, because sometimes there will be extra information that we may not need to solve for the problems, just to test if we really understand the physics problem really well. So here we need to find how many oxygen molecules, and let's just say symbolize it. In physics, we have the big N to stand for the number of molecules or particles, and in this case that should be oxygens, right? So how can we find it? And we in this topic, so let's just review a little bit about these problems here, the concepts here, that the big N can be related to the little n. They are two different things, okay? They're different from each other. Little n is like the number of moles. So what is mole? So like instead of like measure the amount of particles of molecules in like one molecules, two molecules, because we know that they're very tiny, so we can see that there will be a lot of them, and instead of measure them in particles, we measure them in moles. So in order to do that, we have a definitions of a mole. So one mole will have this much, okay, this much molecule, which is about 602 billion of trillion of the molecules. So you can imagine there will be a lot of them, that if we just represent them by each dot here in just a specific volume, then that will be that much of them, okay? And then we can relate it, the number of the molecules by the number of moles through this equation. And so if we want to find the n, we just simply have the little n times with the Avogadro numbers, right? This value is the Avogadro number, which means the number of molecules in one mole. So basically, if we got to know the little n, then we can find this one. Okay, and for this topic related to ideal gas, we have this equation. This is the equation of state, which tells us the relationship between the pressure of the gas, the volume of the gas, the temperature of the gas, that should be measured in Kelvin. Okay, the T here should be measured in Kelvin. If you use other values in different temperature scale, it will be wrong. And then we have this one as the ideal gas constant. Or if there's just some adjustment, then we can also like find the n directly from this equation with the Kb as the Boltzmann constant. But usually I think that in the book, college physics, they just give you this, they just introduce you this equation instead of this one. So we will need to find the letter n, and then we can find this one. So can we find the letter n here? Let's see about this problem. We see that you get short of breath when you get to the top of the mountain because a lot of things have changed in the gas here. The pressure here is less, much less. And then you got the temperature here, you got the pressure here. So in order to find the n, we should know the volumes, right? Yeah, so can we find the problems of the oxygens? We know that average breath will be this much liter, and then 21% of it would be oxygens. Yes, so from here, we can find the volume of oxygens, right? Which will be 21% of this much, right? Of this V here, okay? So if we got this one, and then if we apply this equation, then we can find the n, right? Okay, sounds good, right? Just keep in mind that the T should be in Kelvin, so we have to convert it. The atmosphere, it's up to you if you use the ideal gas constant to be which value. It depends. If you use atmosphere, you use liter, then you have a different values for gas, the gas constant. But if you use Pascal, you use meter cube, then you have a different value for the R constant, okay? So let's try yourself to solve this problem, and then we will see each other in the next video to see how to solve it specifically, okay?